We're going to take a look at multiplication of matrices, and then we'll look at finding inverses of matrices, and they'll undo multiplication for us. In terms of multiplication, there are two types. One is a scalar multiple. The second one is multiplying two matrices together, so a matrix times a matrix. A scalar multiple, a scalar is just a fancy way of saying a number or a constant. A number or a constant, just a good old number that we want to multiply a matrix by. And then a matrix times a matrix, that's where we have two arrays of numbers of compatible size, and we'll talk about that we're going to multiply together in a certain way to get the correct entries. Let's go ahead and start with scalar. Scalar, so we're going to multiply a matrix times a number. So number times matrix is kind of what we're looking at. So say we've got an array of numbers, and this array of numbers describes, maybe labor costs and material costs. And there's been some kind of an increase, and we're going to multiply all of those. This would be a huge increase, but we're going to multiply all of those by 2. Maybe it's inflation, and we're going to multiply it by inflation, but I'm going to stick with the nice number 2 instead. Let's give ourselves these entries of 1, -1, 3, and 4. Okay, so just taking it out of context here. To multiply, we multiply entry-wise, just like we had added entry-wise and subtracted entry-wise. If I'm multiplying or scaling this matrix up by 2, I need to multiply each of my entries by 2. So scalar multiplication. So nice, very easy. And as we multiply each entry by 2, we get 2, -2 for the top row, and then 6 and 12. Oops, 6 and how about 8 for the bottom row. Okay, so scalar multiplication. Let's do one more example. Let's say that we want to take 1/3 of this matrix, all of the entries. So we're going to do 1/3 of, let's do 3, and then 30, -2, and 6. So again, multiplying the scalar by each of the entries inside the matrix, we end up with 1/3 of 3, which is 1, 1/3 of 30, which is 10. So I'll write out what I'm doing here. 1/3 times 30 gives me the 10. 1/3 times the -2, just leaving that as a fraction, is -2/3. And then in my last entry, I've got 1/3 times 6. And if I reduce, I end up with a 2. So that is scalar multiplication. We can also then talk about, what I really want to talk about and spend some time on is matrix multiplication. So our second topic, matrix multiplication. This one has further reaching applications, and it allows us to multiply an array of numbers by another array of numbers. Maybe we've got information in terms of labor and building materials, and we want to offset those not just in one way but in many ways, in terms of inflation and decreasing gas prices, and we've got several different variables that we want to play. So to take, again, ourselves out of context, to give our things just something a little easier to work on, when we're doing matrix multiplication, I want to start by reviewing the size of a matrix, or we call that the dimension. The matrices that I worked on in the last two examples were both 2 by 2 matrices, 2 by 2. We do rows first, so that's 2 rows by 2 columns. Okay, both of those were 2 by 2 matrices. If I were to give you an example of, let's do a 2 by 3 matrix, that means I've got 2 rows and 3 columns. So with 2 rows and 3 columns, I would need something like this, 1, 2, 3, 5, 4, 2. So I've got 2 rows and 3 columns. So that would be a 2 by 3 matrix. If I were to give you something like, let's do a 3 by 1 matrix, that tells me I've got 3 rows and a single column. So I could give you a matrix like this one, 2, -2, and 4. the two matrices that I've given you in a certain order are compatible. If my matrices are compatible for multiplication, that means that when I multiply them together, I've got a 2 by 3 matrix. I need to be able to have enough entries to fill in when I go through the algorithm. Okay, so you'll see what I mean in just a second. 3 by 1 matrix. I know that these are compatible because the interdimensions, the 3 and the 3, match up. So I know it's compatible. And my resulting matrix is going to be a 2 by 1. 2 by 1. Let's multiply these together. You'll get used to the algorithm. It's a little bit much to get used to though, so I want you to watch me really, really carefully as I multiply these two matrices. You really need to practice this and know what you're doing. Okay, so I can take the 2 by 3 matrix, which was 1, 2, 3, 5, 4, 2, and I can multiply that by my 3 by 1 matrix, 2, -2, and 4. I know that I'm going to end up with a 2 by 1 matrix, so 2 rows and 1 column. So I can give myself a matrix, which will be my resultant matrix, that has 2 rows, and I'm going to leave some room because I want to write out my, my math, and a single column, but I'm going to extend it here so that I can write my math. Okay, so 2 rows and 1 column. Okay, here we go. When I start by multiplying these, what I'm going to do is I'm going to take the first row's entries and multiply those by the first column's entries. So I'm going to take, I guess I should use my yellow, I'm going to take these times these and then add them together. Just a new algorithm, you'll get used to it. So I'm going to go 1 times 2, so 1 times 2, plus, I move down and over, 2 times -2, plus 3 times 4. 3 times 4. Let me do the bottom one, and then we'll add it together to get that 2 by 1 matrix. Okay, so now the bottom one, now we're going to move over and we're going to do row 2 times the first column. So I've got 1, I should call that column 1. Okay, and I'm adding them together. So I multiply the entries, 5 times 2, which is 10, but I'll write it out so you can see where it came from, plus 4 times -2, 4 times -2, plus 2 times 4. What I end up with is that 2 by 2 matrix. See, this is 2, -4, plus 12, so that's 14 minus 4, so that's 10. And then in the second row, I've got 10, a -8, and an 8, so this is also 10. Okay, so again, I've got a 2 by 3 matrix. I multiplied that by a 3, right? 3 rows, 1 column. These are compatible, and I ended up with my answer, which is the resultant matrix, a 2 by 1 matrix, 10, 10. There's so many applications here, but we're just going to stick with the arithmetic for now. Okay, let's do another one. Let's do this one. So I've just got some examples next to me here. Let's do this next one. So for example, we're going to take 3, -5, -2, 2, and multiply that by the matrix 6, 4, -1, 9. Okay, the first thing I do is I check for compatibility. I've got a 2 by 2 matrix that I'm multiplying by a 2 by 2 matrix. I want you to pause for just a second, and I want you to answer 2 questions. Are they compatible? Okay, is that multiplication even possible? And if so, what is the dimension of my resulting matrix? Okay, so I want you to think about that. Are they compatible, yes or no? And if they are, what's the dimension of the resulting matrix? Okay, if you're not there yet, go ahead and pause, and then come back when you think you've got it. But I'm going to go ahead and answer those questions. Are they compatible? Yes, because these inner dimensions match up, the 2 and the 2. So are they compatible? Yep. Yes, the dimension of my resulting matrix is what's left on the outside, so that's going to be a 2 by 2. Okay, so I get a 2 by 2 matrix when I'm done. I'm going to do this one in general first so that you can see how everything lines up. As I'm multiplying these together, I'm going to start by taking row 1's entries times column 1's entries. So this is 1, comma 1, okay, right, row, column. Then I'm going to take row 1's entries times column 2 in the next matrix. Okay, so again, row and column 1 and 2. And then I'm going to go ahead and move over to row 2. I'm going to multiply that by column 1 in the second matrix, and then I'm sticking with row 2, and I'm going to multiply that by, I'm just going to put a little arrow here, this isn't my answer. Okay, so row 2 gets multiplied by column 2. So you can see how I'm covering all of my entries and all of the combinations, but that's how I end up multiplying those two together. I'm going to cover up these questions that I had for you, and I'm going to go ahead and move on to the resulting matrix. Okay, so as I multiply these together, I need to do row 1 times column 1. Okay, row 1 times the entries in column 1. I'm going to write them out again so you can see where this comes from, but you'll get quicker at it. So easy to make a mistake though, where you can go right to the answer, but I think writing it out is worth it. Okay, so that means I've got 3 times negative 6 plus negative 5 times negative 1. Okay, that's all I've got for the first entry. Now I move over to the next entry. Remember, this is a 2 by 2 matrix, so I've got to do 4 entries for this matrix. Okay, so I'm in row 1, column 2. So that would be 3 times 4 plus negative 5 times 9. Okay, we'll do the arithmetic next. Now I'm going to go to row 2 of my answer. So I'm going to start with row 2 of the first matrix. This gives me negative 2. I go back to column 1. So negative 2 times negative 6 plus 2 times negative 1. Sticking with row 2. Okay, so still with row 2. Now I'm going to use column 2. That's going to be negative 2 times 4 and then plus 2 times 9. Okay, let's do the arithmetic. Whew, okay, just a lot of work. So this is, let's see, negative 18 plus 5. It's going to be negative 13. And then this is 12 minus 45. So 12 minus 45 is negative 33. Negative 33. Then I get 12 minus 2. Okay, that one's easy. That one's going to be a 10. And then over here I get negative 8 plus 18. That one's also 10. So this is my resulting matrix. Not all of these are compatible, so you have to be really careful when one isn't compatible, that you're not doing the multiplication anyway. I want to do this, this multiplication just one more time, and I'm going to switch these. So this is A and this is B. I'm going to switch this and do instead B times A. Let's rewrite it. B would be negative 6, 4, negative 1, 9. And A is 3, negative 5, negative 2, and 2. I can switch it because they're still compatible. 2 by 2 times 2 by 2. Those inner dimensions match, and I'm going to end up with a 2 by 2 resulting matrix. If I go back to the first example, I'll finish this one in a second, and I call this A and B, and I tried instead to do B times A. I'm not even going to write the matrices out, but my column matrix would go here, and then this 2 by 3 matrix would go here. That would give me B. B is 3 times 1, or 3 by 1 matrix. A is a 2 by 3, 2 by 3. The inner dimensions do not match, so you can't get a resulting matrix out of here. So I would say that this one is not possible. Okay, but the one that we just reversed. So matrix multiplication is not commutative, but I am able to reverse these two. Okay, so let's tackle it again. I'm going to start with row 1 for the first two entries, and I'm going to multiply through column 1 and column 2. Okay, here I go. I will write it out. -6 times 3, if I have enough room, plus 4 times -2. And then the next one, back to row 1, -6 times -5 plus 4 times 2. Lost my spot there. Okay. The other two entries come from row 2. So now I'm going to multiply row 2 through columns 1 and 2. So that's going to be -1 times -2 plus, oh, whoops, I made a mistake, didn't I? I need to do -1 times 3. If you're watching, I hope you caught that. So -1 times 3 means you're getting it if you caught it, plus 9 times -2. Again, row 2, but now times column 2. So that's going to be -1 times -5. And then I move over here, plus 9 times 2. Okay, what do I get? This is -18 minus 8. So that's going to be -26. This is positive 30 plus 8, which is 38. Down here I've got -3. Now that I fix this one, minus 18, which is -21. And then 5 plus 18, which is 23. So I've got my answer. And if you take a look, can I get them both on the same screen? It is not the same as my last answer. So even though I can reverse the order A times B or B times A, does not mean that I get the same thing. So matrix multiplication, again, is not commutative. Commutative means you can change the order. And you can change the order, but you're not going to get the same answer. Okay, let's do another example. Let's do 3 and 4. So I have, can you see the dimension on that one? 1 row and 2 columns. So this one's going to be 1 by 2. I want to give you one that works. So I'm going to multiply this by 1, 0, 0, 1, which is a 2 by 2. This looks familiar, right? We got this when we were solving systems using matrices, and we really wanted that so we could read off the values for x, y, and z. You're going to see it at work again here. I know that we can multiply these together. These are the same, which means I'm going to end up with a 1 by 2 matrix when I'm done. Okay, let me rewrite those. 1, 0, 0, 1. Okay, a 1 by 2 matrix when I'm done. So I want that guy. So I'm going to take the first row, there's only one row, 3 times 1 plus 4 times 0. That's 3. Okay, 3 times 1 plus 4 times 0. Now I'm going to go back to this row, but now the second column, 3 times 0 plus 4 times 1. 3 times 0 plus 4 times 1, so you can follow it. Did you see what we got? We got the same exact matrix. I'm going to do one more with this 1, 0, 0, 1. Let's take a 2 by 2 this time. 6, -2, 4, 7. Just making one up. And I'm going to multiply that by 1, 0, 0, 1. Okay, we've done these 2 by 2s, and we know what they lead to, but let's double check it. They're compatible, and I'm going to get a 2 by 2 matrix when I'm done. Okay, so answer is going to be a 2 by 2 matrix. Okay, so now I'm going to do the first row. So that's going to be 6 times 1 minus 2 times 0, so that's 6. 6 times 0 minus 2 times 1, minus 2. Okay, so the first row here gives me the first row of answers. Looks familiar. Second row here is going to give me the second row of answers. 4 times 1, 7 times 0, that's 4. 4 times 0, 7 times 1, that's 7. So again, I am being given the same matrix back. Well, what we call this matrix, 1, 0, and there are many versions of this, 0, 1. This is called the identity matrix, that's capital I. It's called the identity matrix, capital I. When we use just regular numbers, the identity is 1, right? So for example, 5 times 1 equals 5. Well, here we're working with a matrix. I'll call it matrix A. So I can say that matrix A times the identity matrix I gives me matrix A back. So that's my identity matrix. If that's true, I should be able to get to the identity matrix. We had inverses, so this is the identity, but we also had inverses in multiplication, in addition. But if I wanted the inverse in multiplication, I multiplied by the reciprocal. So 5 times 1/5 equaled 1. It got me back to the identity. So 1/5 would be the inverse of 5. You could say 5 is the inverse of 1/5. Matrix A also has an inverse. And that inverse, I'm just going to call it A inverse for now, would be the matrix that gets me back to the identity. So this is just notation for A inverse. The matrix that I can multiply to get back to matrix I. So we want to be able to calculate the inverse, and it's really helpful when we're calculating or working with a matrix equation, and we want to be able to solve not a system of equations, but truly a matrix equation. Here's an example of one that we're not going to actually create the matrix, but we're being asked if one matrix is the inverse of the other. So here's the question. So example is, I should say R, because there's two matrices. Are A and B inverses of each other? Okay, so what would that mean, inverses? That would mean that A times B equals the identity matrix, and B times A also equals the identity matrix. Let me see that. So are they inverses of each other? So let me give you the matrices. A is 2. No, I'm not going to do that one. Sorry, wrong example. A instead is 3, -7, -2, 5. And B is 5, 7, 2, 3. You cannot tell by looking at matrices if they are inverses of each other, unfortunately. So instead, we're going to go ahead and multiply these products out and see what we get. Okay, here we go. A times B. They're compatible. 3, -7, -2, 5. Good way to practice also with your multiplication. See if you get that down. It's going to be a 2 by 2 matrix when we're done. So I want the first row to give me the first row of answers here, and I'm going to multiply those by column 1. Okay, so 3 times 5 is 15, plus that would be a -14. 15 minus 14 is 1. First row again gives me the first row of answers, but now times column 2. So that's going to be 3 times 7, which is 21. Minus 7 times 3, which is 21, so that would be 0. Okay, now row 2 is going to give me the second row of answers in my resulting matrix. So now I'm going to take -2 times 5, that's -10, plus 10, that's 0. Okay, looking good. And then -2 times 7 for the final answer entry, -14 plus 15, -14 plus 15 is 1. Okay, so far so good, but we need to go in both directions. B times A. Okay, if you do not have your matrix multiplication down after these, you've got to be really, really close. Okay, so we're looking for that 2 by 2 matrix. The row 1 of our resulting matrix comes from the row 1 of the first matrix. So times column 1 first. This is going to be 15 minus 14, that's 1. And here we've got negative 35 plus 35, which is 0. Okay, now row 2, to get row 2 of our resulting matrix. Back to column 1. 2 times 3 is 6 minus 6 is 0. 2 times negative 7 is 14 plus 15. So negative 14 plus 15 is also 1. So the answer is yes. A and B are inverses. Let's find some inverses. So that's really the last task we've got in the 2-4-2-5 homework, is finding an inverse. You have just a couple of problems on it, and it uses the row operations that we used previously. And we're going to use an augmented matrix as well. So we have A, and we want to find A inverse. I'm just going to go through the algorithm, and it is an algorithm, but it's going to seem somewhat familiar to you. Matrix A is 4, 2, 2, 4. To find the inverse, we're going to augment A and the, let me do that again, A and the identity matrix. I was going to put an I next to an I, but this is what we want. So we take a big matrix, we put matrix A first, and then on the other side we put 1, 0, 0, 1. Our goal is to use row operations and get the identity matrix on this side. So we're going to use row operations to get 1, 0, 0, 1. And then what we're left with on this side is A inverse. It's really interesting if you want to do a little more researching on it, but what we're actually doing is we are undoing the steps from matrix multiplication. I'm not going to go into that much depth, but as we go through the algorithm, that's what we end up doing. Okay, so our goal is 1, 0, 0, 1. And what we want to come up with is a 0 in this spot and a 0 in that spot. So I'm going to go ahead and start with my row operations, and I'm going to get a 0 in that spot first. So I'm going to keep row 1, but I'm going to take let's do 2 times row 2 and subtract row 1. So the 4, the 2, the 1, and the 0 can stay. But we're going to go 2 times row 2. So 2 times row 2, you see it there? 2 times row 2 will be 4 minus 4, and that's going to be 0. I'm going to do 2 times row 2, which is going to be 8 minus 2, and that gives us 6. On the other side as well. So 2 times row 2 is going to be 0 minus row 1, negative 1. Again, 2 times row 2, so that's not going to be 2 minus 0, which is 2. Okay, so we're multiplying row 2 by 2, and we're subtracting row 1. So we've got 2 operators there at the same time. My next goal, and your steps will be the same every time, is to get a 0 in that position. So to get a 0 there, do you see what I need? I need 3 times this row, which is row 1, and I'm going to subtract row 2. So not a bunch of steps, but enough, where you've really got to keep track. So 3 times row 1 minus row 2. I'm going to keep row 2. So I keep the 0, 6, the negative 1, and the 2. So now I'm going to take 3 times row 1. So for the 4, that's going to be a 12 minus 0. So 12. 3 times row 1, so 3 times 2 is 6 minus 6, which is going to be 0. And here I'm going to take 3 times row 1, so 3 times 1 is 1, minus negative 1 is going to be 4. And then 3 times 0 is 0, minus 2 is negative 2. Okay, you got it? So far so good. I'm really combining 2 steps. I'm multiplying a row and then subtracting another row. But you've got 2 different iterations of that so you can follow it. Look how close I am. Remember what I wanted was 1s down the diagonal and then 0s here and here. What I really need to do is just 2 final row operations. I need to take 1/12 of the first row and then 1/6 of the second row. So we're going to take 1/12 of row 1. 12 divided by 12 is 1. 0 divided by 12 is 0. 4 divided by 12, if I reduce it, is 1/3. -2 divided by 12 is -1/6. Okay, so again, these little guys right here, this is 4/12. And this guy right here is -2/12. And I want a 1 there instead of a 6. So I'm going to take 1/6 of 1/6, I can't say that today, 1/6 of row 2. Okay, 0 divided by 6 is 0. 6 divided by 6 is 1. Okay, we're there, right? -1 divided by 6 is -1/6. 2 divided by 6 is 2/6, which is 1/3. So this guy is 2 divided by 6, right? -1 divided by 6, and so on. Okay, what we have, maybe you're not as excited as I am, but what we have is A inverse. I have the identity matrix now on the other side, and what I have here on the right-hand side is, lo and behold, A inverse. And you can check it. Gosh, I'm really tempted to, but I don't think I will. I know I've got the right answer. I'm really tempted to check it, but I don't think I will. You could check it, though. I want to tell you how you would do that by doing A times A inverse. You could also, if you wanted to, do A inverse times A. Those should be commutative. So I would do this. I'm not going to, because I want to do another example. And if I multiplied these out, -1/6, 1/3. If I did my matrix multiplication, I would, lo and behold, get the identity matrix. I want to do another example, though. I do want you to know, as we're moving through all these examples, I'm only doing 2x2 examples. There is a 3x3 identity. And I'm only doing 2x2 examples because that's all I'm giving you. So that's really nice of me, right? So we have a 3x3 identity. We have a 4x4 identity. But all of our identities are square matrices. So 4x4, we could have a 5x5. Those are all of the matrices that constitute those identities. But I'm not going to give you any 3x3 matrices where you're finding an identity. Let's do one more. I want to find A inverse. A is 3, -2, -7, 5. If I'm finding A inverse, I want to augment matrix A, -2, -7, 5, with the identity matrix, 0, 1. My goal is to get the identity matrix on this side, and then I will be left with A inverse on the other side. So my goal is to get 1s down the diagonal and 0s in the other places. Okay, so I want to start by getting 0 in this position right here. Gosh, not just a simple multiplication, but think back to your elimination days. I want a positive and a negative value, I'm going to do it that way anyway, that have the same like coefficient as what these are. So 3 and 7 have a common multiple of 21. So I am going to take, let's leave that first. It's kind of like a common denominator, right? Common multiple. I'm going to take 7 times row 1. I already have a negative sign there, so I don't need to subtract. I'm going to add 3 times row 2. Okay, so here I go. 7 times row 1 would be 21. Plus 3 times row 2, 3 times -7 would be -21. So that would be 0. 7 times row 1, that would be -14 plus 15. Oh, nice. Okay, so I get a 1 there. Super nice, right? I have the first row of my identity. And then over here, I want 7 times row 1, which would be 7, plus 3 times row 2, that would be 0. So 7. And then over here, 7 times row 1, 7 times 0 is 0, plus 3 times that original row 1, 3 times 1 is 3. Okay, my next goal is to get 0 in the other spots. Okay, so I start by getting 0 in the lower corner, then I'm going to get 0 in the upper corner, so I really want to get 0 here. This 1 makes it super nice. I want to keep that lower row, 0, 1, 7, 3. To get this one to be 0, I want to add, I've got a -2, I want that to be 2. So I'm going to take row 1, and I'm going to add 2 times row 2. Okay, are you ready? This goes with that guy up there. Row 1 plus 2 times row 2. That would be 3 plus 2 times 0. So I get 3. Row 1, which is -2, plus 2 times row 1, plus 2, which is 0. Perfect. I keep going, though. I want row 1, which is 1, plus 2 times row 2. So 2 times 7 is 14. It's 15. And then I want row 1, which is 0. So 0 plus 2 times row 2. That would be 0 plus 6, or 6. Okay, I'm almost there. Do you see what I've got? I almost have the identity. I just need a 1 here instead. So I need to take 1/3 of row 1. That's going to be my final matrix operation. Aren't these tedious? Super, super tedious. I will only have you do the 2 by 2 examples. Okay, we're almost there. I need to fix this though. So I need 1/3 of row 1. Row 2 gets to stay. 3 divided by 3 is 1. 0 divided by 3 is 0. Don't forget this side. 15 divided by 3 is 5. 6 divided by 3 is 2. So I took care of row 1. I'm going to keep row 2. 0, 1, 7, 3. So what I'm looking at then, because I actually undid matrix multiplication, is the identity and a inverse. Let's check this one. These are nicer numbers. Let's do a times a inverse, and I should get the identity. Okay, so where was a? A is 3, -2, -7, 5. And I'm going to multiply that by this inverse that I found. And I had better get 1s on the diagonal and 0s everywhere else. You ready? Okay, first row here gives me my first row of answers. Let's start with column 1. 3 times 5 is 15, minus 14 is 1. So far, so good. Okay, second row for the next spot, or second column, sorry. 3 times 2 is 6, minus 6 is 0. Excellent. Second row gives me my second row of answers. -7 times 5, that's -35 plus 35. Good. And then -7 times 2, that's -14 plus 15 is 1. Excellent. You could do also another check. These are commutative, and make sure that you get the identity going in the other direction as well. In the next section, we will apply these, but for these 2 sections, it's really just a matter of going through and learning carefully what those algorithms are.